Good morning. My name is Greg Wadley with CTC and Associates, and I'm the Clear Roads Administrator. We're here for the final project webinar for the project entitled Update to Clear Roads 1304, Best Practices for Protecting DOT Equipment from the Corrosion Effect of Chemical Deicers. This research effort is led by Xiaoming Shi of Washington State University. Before I turn it over to Xiaoming, I just want to let everybody know that this webinar is being recorded and that will be posted on the Clear Roads website later this week for viewing by you or your colleagues at your convenience. We also ask that unless you're speaking, please remain off camera and keep your microphone on mute. However, if you have any questions or comments, please enter them into the chat box and we'll address them at the end of the presentation. I think that's everything I needed to say up front, so I'm going to turn it over to you, Xiaoming.
Thank you, Greg. Let me try to share screen. Do you see the presentation?
I do.
Great. So thank you, everyone. And like Greg said, this is the final presentation for the Clear Roads Project 21-02. The title is pretty long. The title is Update to Clear Roads 13-04 Best Practices for Protecting DOT Equipment from the Corrosion Effect of Chemical Deicers. And I'm the leading investigator, but we also have several team members, Moid Jamal, who did most of the heavy lifting in the lab, and then two consultants, Dave Wagner and Paul Braun, also assisted in some of the tasks. Just to refresh our memory why we want to do this project, the project objectives are twofold. First, to produce new data and renewed understanding to update the anti-corrosion coding section of the previously completed project back in 2015. And that project is titled Manual of Best Practices for the Prevention of Corrosion on Vehicles and Equipment. The second objective is to provide guidance to encourage good practices and procedures that may be implemented by highway agencies. Here I show a optical photo of a coating, which is a sacrificial anode or zinc-rich coating under the microscope. So this project has 5 tasks. Task 1 is survey and market analysis. To begin with, we conducted an online survey of Clear Roads member states so that we can capture practitioner insights and collect more detailed information, such as the the use of current deicers, off-market anti-corrosion coatings being used, the metals, typical metals in DOT equipment, and so on and so forth. Now, we certainly want to learn what works well, what doesn't, and limitations of such anti-corrosion coatings, with a focus on several parameters, coating parameters and application methods. Also, we intend to collect data of any sort of field test results, even though, there's very little out there. So as part of task 1, actually, task 1A is the survey, and we were able to obtain 23 complete responses. As you can see from the map, the location of these responding agencies, it's pretty diverse. And from the survey results, you can see that we are having a diverse group of responding agencies, in terms of climate conditions, and pretty much everybody's doing anti-icing, de-icing, direct liquid application, and a little bit of sanding. So if we look at the winter road maintenance practices, again, there's the sanding using pre-wetted abrasives versus dry, and salting or de-icing using pre-wetted salt and dry salt. So we also ask questions related to the use of corrosion inhibitors in these products. And turns out most agencies do use corrosion inhibitors in one way or another, and they mainly use beet juice and also inhibitor included with the magnesium chloride deicers. And we also look at the type of metals typically seen in DOT equipment, And vehicles, as you can see, are carbon steels, stainless steels, aluminum alloys are the more commonly used metals or alloys. Now, in terms of the risk of de-icer corrosion to different components of the equipment, you can see that dump trucks are the highest risk, followed by the liquid de-icer applicators and hoppers, and front end loaders. So now in terms of the specific components, as you can see, the previous one, this one is about the type of equipment, but this other one is the different components. You can see the highest risk or the most susceptible to de-icer corrosion is brackets and supports, followed by frames and fittings and so on. And then we're also looking into how many vehicles, how much equipment asset these responding agencies have to get a better sense. And then look at the typical current practice, how frequently they, for instance, replace a vehicle because of corrosion damage. And it's about, somewhat half and half. And then replacement cycles, typically, you can see the vast majority of agencies end up replacing the vehicle within 10 years. And if we look at the current practice of managing corrosion, then most of them do some practices, such as replacing steel with stainless steel, and some replaced with non-ferrous metals such as aluminum alloys. And the agencies who report not doing corrosion management is due to the lack of expertise or funding, or they use very little salt. Now, in terms of inspection, basically agencies tend to inspect every 6 months or so. The majority of them. So that's the current practice. Now, in terms of washing and drying of equipment of vehicles, yes, most of them, the vast majority of them wash vehicles. And in terms of frequency of washing, again, it seems to converge on, washing after every storm. Now, in terms of drying, actually, most of them don't intentionally dry the vehicles. And the drying cycles, for those who actually dry the vehicles, the drying cycles are somewhat, less managed, I guess, not really managed. And typically it's self-dried, it's not mechanically dried. Or, like the military, for instance, they would have more facility to intentionally manage the drying of the vehicles after washing, but highway agencies don't have that. So when it comes to anti-corrosion coatings, at the time of manufacturing, of course, typically they have various ways of, applying the coating or paint. And after market, or other than the OEM coating system, there are also practices of using coating or some sort of spray-on protection. But again, for those who don't apply additional coatings, there are various reasons, usually dealing with the limitations of facility or staffing. Now, as you will see later, food film is a product being mentioned over and over and over by various northern state agencies. But again, as you can see here, most of them actually, the majority of them don't do anything with coating practice after OEM because of the limitations. Now, you already see fluid film mentioned a couple of times here. In terms of the type of coatings people use, coating is a somewhat loosely defined term. As you'll see later, in the actual experimental program, we also included sealants and grease as a way of coating, and they do provide some level of corrosion protection. So in terms of post-evaluation, also we collected some practitioner information or experience. Usually this is not a rigorous program, applied to manage the post-evaluation codings. So again, we didn't really find any rigorous studies on field testing of anti-corrosion performance of such coatings. So again, most agencies don't really conduct post-evaluation. Now, the second part of task one, or part which is task 1B, is the market analysis. So in this case, we asked more specific questions related to anti-corrosion coatings, such as the types used in the last decade, the methods of application, and so on. So that was intended to identify a list of anti-corrosion coating systems with the best user experiences and help agencies identify the optimum cost-effective coating system choices for their equipment assets. So this helped us narrow down the list and then prepare us for some rigorous laboratory testing under well-controlled conditions. So in this case, the second survey basically had 21 complete responses, and you can see the locations of these agencies responding to the second survey. And here, basically, we identify for different metal substrate, different coatings are used, and the most commonly used ones are like, for instance, Lubrasil, which is a product commonly used for stainless steel substrates, and then fluid film is often used for carbon steel substrates, and a number of products used for aluminum alloys or copper alloys. Like I mentioned, for some of these coatings, quote unquote, then they're loosely defined because the dielectric grease in some other contexts would not be considered as a coating. And armor seal, for instance, is a sealant, which is not truly a coating, but in this project, we have more general definition of coating. So anyway, from the survey, we identified these most commonly used products. You see a small number next to the brand name. For instance, fluid film, we had 4 agencies reporting the use of them on carbon steel. Or dielectric grease, we have 3 respondents, so it's a more common practice. So the list goes on, but then we take another look at different climates, under different climates, such as salty conditions, hot versus cold climate, or wet climate, what type of products are used more often. Again, this is no longer differentiating between different metal substrates, but you can see that fluid film is one of the products keeps showing up. Now, and here, if we look at the most commonly used products in the last 10 years, again, fluid film shows up. But I would argue that salt neutralizers, these products offered by various responding agencies, they're not truly coatings. They're more like a useful product to ensure better cleanness of the metal substrate before you can put on any sort of coating or spray on any sort of corrosion inhibitor. So that's actually a little bit outside of the scope. And paints in this context of the project is considered as coatings. So now we also look at what agencies would recommend as a good coating in terms of being, the coating should last longer, easy to apply, and being most effective. Again, you can see that fluid film is a clear winner from the user experience, positive user experience of these responding agencies. So based on the survey results from task 1, we developed the experiment plan in task 2. So as laid out in the scope, we were supposed to investigate at least 3 different metal types and 3 different coating systems, 2 different deicer types. So we end up choosing a blend of sodium chloride and calcium chloride, and actually another one is a magnesium chloride with beet juice. So the fortunate thing is that there is a well-established lab testing protocol known as the salt spray test protocol under SAE J2334. In that case, this salt spray test protocol incorporates wet-dry cycles as well as exposure to salt, so that previous research had shown that 60 cycles of this accelerated test is equivalent of about 5 years of on-vehicle testing. So with this accelerated lab test, one can greatly reduce the expense of outdoor testing. And maybe that is partially why we couldn't find any field testing results, because the SAE test protocol is pretty reliable. And for each test, we typically use 5 replicates, except in some cases we use 3. So here is some more details. Again, if you look at this table, on the left is the column on materials. We had 4 different metal types: steel, which is basically carbon steel, and then stainless steel, aluminum, and copper. And then for each of them, we select several coatings. As you can see here, this was the list, and then we further finalize this based on consultation with the project panel. And then here's a more detailed table with different test methods as a function of the coating type, the metal alloy type, and then again the different deicers we used. So for instance, in group 1 or series 1, we have used a non-destructive evaluation method called EIS, or electrochemical impedance spectroscopy, which gives a lot of mechanistic detail of how severe the corrosion is and sort of why it's that way. And then the second series of tests is the salt spray test. Like I mentioned earlier, it corresponds to field performance really well. So that's fortunate. And then in this case, for the salt spray test, actually, the series 2 is with the scribed coupons. Basically, you have an X marked on each coated coupon, and the series 3 is without the scribe. Especially in some cases, the coating is too soft, or like just a grease. There's no easy way to do that scribe. So so depending on the situation, there's a little bit deviation from this scribing procedure. And then as a coating on vehicles, sometimes it's really important to ensure the adhesion. So we also test the adhesion and test the hardness. For instance, if it's underbody coating, especially, the coated surface may experience some abrasion by abrasives or sand. So a hard surface will be preferable. So we tested hardness, and there are 2 tests. One is a pencil hardness test, but for the even harder coatings, we end up using the Vickers hardness test. So we also had some naming convention to simplify the figures. So as you can see here, for instance, if we have a figure later shows S-LS, that means we use the steel substrate and lubricil as the coating, and so on and so forth. So task 3 is really the execution of the experiment plan approved by the project panel. And like I mentioned earlier, first test is a non-destructive test called EIS, which gives us a lot of details or insights about what's really going on at that coated surface. Basically, the way it works is you have a metal coupon coated working as a so-called working electrode, or WE, and then you have a reference electrode next to it, and then you have a counter electrode. Between the counter electrode and working electrode, you apply a potential usually, and then you get a current feedback. And these are AC currents or alternating currents. And from the relationship, you can derive, the potential to current relationship, you can derive so-called impedance spectroscopy. And there's a lot of details about this method, but I won't go too much into it. Basically, what we find in the end is, okay, from these figures you obtain from the ES test, then you can analyze the interfaces. For instance, here you see a combination at the top, you see a combination of capacitance and resistance. So this is a simulation or so-called equivalent circuit of the coated metal surface. So for instance, the first resistance is basically the resistance of the solution, the de-icer solution. And then the second combination, which is the capacitance and resistance, is basically an indication of the coating to de-icer solution interface. So in terms of that coating soaked with de-icer, it becomes a non-perfect capacitance or capacitor, and it has its own resistance. And then there's another combination of resistance and capacitance, which is actually in this case, the capacitance is a so-called verbal diffusion. This Q is another kind of capacitance, and this W is a verbal diffusion resistance. Anyhow, these things actually tell you how fast corrosion is occurring at the metal to de-icer interface. So here I mentioned two different interfaces. One is the coating to de-icer interface, and the other one is the metal to de-icer interface. So we can get specific values of these resistance and capacitance, and then from their change over time, we can see whether or not the coating is deteriorating and how fast it's deteriorating, or how fast also the underlying metal is corroding. So the second type of test, like I mentioned, is the salt spray test, which is standardized by SAE, I think it's the Society of Automotive Engineers. And as you can see, there are different cycles. There's a humid cycle for 6 hours, salt spray cycle for 15 minutes, and a dry cycle for 17 hours. And these are conducted at different relative humidity and temperature and time duration as well. So this is just another way of summarizing this. So again, fortunately, there are prior studies demonstrating this kind of accelerated exposure corresponds well to the field performance of coatings. Again, some of the coated metals were ascribed, some were not. So yet another set of tests was the adhesion test, basically pull-off test to measure the adhesive strength of the coating to the metal. And then yet another one is the pencil hardness test, and the Vickers hardness test, which is for the really hard surfaces. Basically, you measure how big is the dent when a 1 kilogram force is applied onto that surface for 15 seconds. And again, we have basically hundreds and hundreds of these EIS results, because at different time over 31 days, we measure them periodically. And this gives us a lot of insights in terms of how the coating deteriorates and how the corrosion propagates, or initiates and then propagates. So this is just one example, a steel coated by Lubrasil, and in this sodium chloride and calcium chloride mixture de-icer at day 30, and this all the ES results, and then we can derive these parameters. Again, the most important thing we want to look at here is this RPO, which is the pore resistance. Basically, the coating under microscope is highly porous, even though with our naked eye, it looks very impermeable. So the de-ices penetrate and saturate that coating, and over time, this resistance drops, and that's an indication of that coating failing itself over time. Now, another parameter is this charge transfer resistance or polarization resistance, which is how fast, which is the resistance of the metal to de-icer corrosion. So the higher the resistance, the better the metal is resistant to the de-icer attack. So to evaluate coating performance, we mostly use the RPO. So the higher, the better the coating is. So here, as you can see, this is a very busy chart. So this is pore resistance for day 1 versus day 30. Day 30 is the curve, and day 1 is the bar chart. And the x-axis is basically the combination of coating and the metal and the coating. So if we consider we need a coating which gives us really high pore resistance, both at day 1 and day 30, then the best product we found was fluid film for the aluminum substrate. And following that is the Aquapon, which is a zinc-rich epoxy primer for the carbon steel. And then by Lubrasil on stainless steel, and then DoxIT for copper substrate. And this is only for the sodium chloride, calcium chloride salt blend. If we look at the magnesium chloride beet juice blend, somewhat similar. You see some clear winners like fluid film. Here again, fluid film for both aluminum and carbon steel substrates, and then Lubrasil for stainless steel substrate, and then dielectric grease for copper substrate. Now, with such information, then we can rank the different products. For instance, you can see here for steel, the best products are AP, FF, LS, Lubrasil, fluid film, and Aquapon. For stainless steel, is Lubrasil and Armasil, and so on and so forth. So these rankings are different actually for the 2 different types of de-icers. So if your vehicles are exposed to both types of de-icers, then we have to consider both. Now, the good news is that for the cyclic salt spray test, most of the coatings pass the test. What that means is by the end of 60 cycles, which is equivalent of 5 years in the field, they do really well. In other words, you don't even need to reapply them every 5 years. Of course, in practice, most agencies end up reapplying them every 3 to 5 years just to be safe. But there are a few samples failed the 5-year test. For instance, the Lubrasil on carbon steel surface. Again, Lubrasil is a sealant, so it's not intended to be a long-lasting coating anyway. And also the DO and DG, I think the full text here, basically the dielectric grease and the DoxIT are 2 lubricants. They, again, are not intended to be anti-corrosion coatings. So they didn't really pass that 5-year test or 60 cycle etc. test. So as you can see from a few selected images by day 31, those coating metal combinations that pass the test look really well, no significant rust. But for those who failed the test, there are like the Lubrasil on carbon steel, and B is just because we have 5 replicas A, B, C, D, E. So this is one of them, and you can see clearly there's significant rusting And then we use the software to quantify the percent of rust area. And then also we rate the creepage, which is another indicator of how severe the coating is failing. And again, fortunately, most coatings worked well. So as a summary of the data analysis, if we look at also the adhesion test, Aquapon, which is the zinc-rich primer, showed the highest adhesion strength. Keep in mind, the Lubrasil or Armasil were just sealants, so not very strong coatings. So in this case, again, the Aquapon was the adhesion strength on average was more than 1,400 psi, while the other Armasil on aluminum or stainless steel was around 400 to 500 psi. Now, for the Lubrasil, one challenge was the glue didn't work well on the substrate, so we couldn't get good results. Now, in terms of pencil hardness test, the vast majority of the coatings were just too soft. The only exception was this sacrificial anode, which is a brand name is Aquapon, which is zinc-rich epoxy primer and sufficiently hard. In fact, we had to add additional load to be able to measure its hardness with pencil hardness test. Otherwise, it will be too hard to measure. And again, this is no surprise because this is a very much zinc-rich primer, so its hardness is similar to a galvanized surface. To conclude, the abrasion resistance and resistance to scratch and indentation of Aquapon is much higher than any other tested product. Also, because the zinc-rich, if you have a scratch, the zinc is supposed to pump electrons towards that defect, so it has self-healing properties. This can reduce the cost of reapplication, but this product is having higher initial costs, around $225 per gallon, so about 400 times higher than, initial cost 400 times higher than fluid film. And because it's a traditional coating, so requires very rigorous surface preparation of the metal surface. On the other hand, fluid film is lightweight, inexpensive, versatile, doesn't require very rigorous surface preparation of the metal. And one lesson learned is also keep the vehicles dry when they're not in use, after they're being washed and there's no residual salt. So that could extend the service life of the equipment assets. So from the data analysis, we also prepared some comparison charts for the tested products. For instance, just a few highlights. Again, fluid film has a lot of advantages. No really rigorous need for cleaning or surface preparation, while the Aquapon requires serious, rigorous surface preparation. But for Aquapon, one benefit is, again, it could easily last 3 to 5 years without any sort of reapplication or repair. Now, for the sealants, Lubrasil versus Armasil, you can see here, Armasil worked better, especially for the surface tested, like aluminum alloys and stainless steel. It can last 3 to 5 years. In other words, they pass the cyclic salt spray test. But for Lubrasil, the service life is only about 6 months on steel. Now, for the dielectric grease and other lubricant, again, the benefit is you don't need special surface preparation, but the downside is they both fail the 5-year test. So you need reapply whenever necessary. Now, if we look at Aquapon again, one significant benefit is its abrasion resistance and also self-healing properties. Now, for fluid film, it's just a different type of application because no need for rigorous surface preparation, but we still, well, it's actually quite surprising we find it being able to pass this 5-year test. Now, again, for the sealants, they just don't have, they're not designed to be abrasion resistant. So you basically cannot trust them for underbody applications. For the lubricants, again, they're not supposed to have abrasion resistance, but since they can easily creep into adjacent area, so it's a different kind of product than the traditional coatings. So with this kind of information, both from the survey analysis and the rigorous laboratory testing, we were able to update the manual, especially for the section intended to be updated. So again, it's more a repackaging of the information in a more user-friendly fashion. So I won't repeat this, but one interesting thing is that we also updated a small section on the use of corrosion inhibitors because it seems like the products with the beet juice tend to have much less rust on them. And even for the copper coupons, it's also showing the same phenomenon. The benefit of having corrosion inhibitor incorporated with the deicer. But of course, there are spray-on corrosion inhibitors for the vehicles themselves. But again, that's outside the scope of this project. We also added a few things or updated a few things on washing and drying. And that's all. And I welcome your questions. Let's see.
All right. Thank you, Xiaoming. I appreciate your time and presentation there. So we don't currently have any questions in the chat box, but Clay Adams is now raising his hand. Go ahead, Clay.
Xiaoming, what can you tell me the mag chloride beet juice, what percent? We add some beet juice to our sodium chloride brine, but can you tell me a little bit about that mix?
Right. It's not top of my head, but I would say the most common mixes we've seen are not added to the mag, right? The typical add is chloride, and usually at 8 to 20 volume ratio. But in this case, again, this was part of the decision, I think, to cover enough scenarios, both sodium mag and calcium without having to double the number of experiments. So I have to go back and look at the original notes. I think this was 90 to 10 volume ratio, but I need to double check.
I'm just curious, did Clay, did that response come through clear for you, or was it broken up?
It's pretty broken up.
Okay.
So maybe there'll be something in the report. I'm just, I know we buy our beet juice straight. I do know that they sell beet juice with a small percent of mag chloride mixed in with it, like 10% mag chloride to 90% beet juice. But I'm just curious what it was that they were actually testing these coupons against. We don't think we get any anti-corrosion effort from the 10 or 20% beet juice we put in our sodium chloride. But his last comment there kind of indicated that maybe there is some corrosion inhibition by using beet juice. So I'm just curious what it was that they were testing.
Right.
Xiaoming, you're just so you know, maybe right now your camera is off. It might be best to leave it off because, like I said, it was pretty broken up.
Sorry about that. Can you hear me better when I move closer?
Yes, thanks.
So what I want to say is, yeah, I need to track down this detail, whether it was a 90-10 or 80-20 volume ratio in terms of mag to beet juice. But from our previous studies, I mean, many of our other publications, basically consistently showing that beet juice is a very effective corrosion inhibitor. So it does, I mean, add value in that regard.
Thank you.
All right. Does anybody else have any questions? Feel free if you want to, if you do have a question or comment, just go ahead and speak up or raise your hand. All right. Well, thank you for your time today. Just to let you know, this project, this was the final deliverable on this project. The report will be posted on the project page, as well as this the manual that came out of this, as well as the this webinar recording. So I will alert you guys to when those things are all posted, so that you can review them at you know, at your convenience. But also until then, all the interim deliverables are, of course, on the members page, and you guys know where to find those on the research project documents. So thank you again for everybody attending today. Have a great rest of your week, and we'll talk to you soon.
Thank you, everyone.